So after introducing the big still just measure, and then we talk about how we can approximate a set E who is the big still just measurable set, and then we talk about how we can approximate the measure of E using not only the H intervals but open intervals, and later we also show that we can approximate that measure using the measure of open sets where the open set contains E, or it can be approximated by the measure of compact set where the compact set is the subset of E. And moreover, there are another approximation theorem which says that, so notice that before the approximation is like we approximate the measure of E using the measure of open set, or using the measure of compact set, or using the measure of open intervals, or using the measure of H intervals. Now in this proposition, it's a little bit different. So the followings are equivalent. So E is mu M mu F measurable, which means it is the big still just measurable. If and only if E is equal to G delta set minus N1. Okay, so let's call this V. V is countable intersection of open sets, and the measure of N1 is equal to 0. We can also write E is equal to V, let's see, VH, okay, union N2, where H is F sigma, countable union of closed sets. And mu of N2 is equal to 0. Okay. So observe that if E is equal to V set minus N1, we already know that because this is belong to G delta, right? And the G delta is a countable union of open sets. And of course, this is inside of M mu F, because M mu F is sigma algebra, and each open set is definitely inside of M mu F, and it's closed under countable intersection. Okay. And we also have this, right? This is a null set. Because by the completeness of M mu F, this is also in M mu F, since mu F of N1 is equal to 0. Okay. And similarly, E is equal to H union N2. That also implies that the E is in mu F. So what we going to prove is first, given that E is mu F, that implies E is equal to V set minus A1. Okay, so how do we and E is equal to H? We're gonna prove them at the same time. So we're gonna use theorem 1.18 implies that for every J in N, okay, there exists Uj that contains E such that mu of Uj is smaller or equal than mu of E plus 1/2 to the power of J. And similarly, there exists Kj that is a subset of E such that the measure of Kj is going to be larger or equal than the measure of Ej minus 1/2 to the power of J. And together we can say that mu of E is smaller or equal than mu of Kj plus 1 over 2 to the power of j larger or equal to the mu of u minus 1 over 2 to the power of j. Okay, and then so we have a claim mu of sorry, we have a define or denote v. So notice that it actually gives us a hint in the statement. So because of because v, we're given that v is in g delta, that means, and here we already have like a countable collection of open sets, and because delta implies intersection, so that kind of like give us an idea like how to define the set v. So we're gonna define v to be equal to the intersection over j of uj, and the h to be the union of j of kj. Okay, so the v, and what do we have? We have that h is a subset of e is a subset of v. Okay, so we're gonna do a claim that mu of h is equal to mu of e is equal to mu of e. So let me do it one by one. Okay, so we already have mu of h is smaller or equal than mu of e. So trivial. Okay, how to prove the other direction? So mu of h, okay, is equal to mu of the union of kj. Okay, and I'm going to erase this for now. So notice kj is an increasing sequence of sets. Okay, if it's not, then we can make it as so. Okay, so the limit as so we have what we already have this inequality, right? And then this inequality implies the limit as j goes to infinity, mu of e is smaller or equal than the limit as j goes to infinity, mu of kj plus the limit as j goes to infinity 1 over 2 to the power of j. Okay, and then what is this? Well, because it's increasing sequence of sets and using the continuity from below, we have mu of the union of kj, and this is equal to mu of h, okay? And this is just equal to 0. So what do we have? We have mu, and then this one does not depend on j, so it's just mu of g, mu of e. Mu of e is smaller or equal than mu of h, okay? And then because we have this earlier, and now we have the other direction, and then we have down. So on the other side, on the other hand, again, we have e as a subset of n, of v. So mu of e is smaller than mu of b, and then we just need to show the other direction, right? So okay, and then again, we have these inequalities, which is very important. So I'm going to highlight this inequality, okay? And this inequality is derived from theorem 1.18. So we have this, and then we add a limit on both sides, j goes to infinity. And the limit j goes to infinity of mu of e, and then this one does not depend on j, so it's still going to mu of e. And then for this, let's see, j, because uj's are decreasing sequence, so we have mu of intersection of uj minus 0, which is mu of v is smaller than mu of e, and together with, so these two gives us the equality. Okay, therefore we're done. Therefore, mu of V is equal to mu of E is equal to mu of H. Okay, and then that implies mu of V set minus E is equal to 0. Hence, let N1 to be equal to V set minus E. And we also have mu H, E set minus H is equal to 0. So let N2 is equal to E minus set minus H. Okay, and then we're done. So notice that here we use the assumption that the measure of E is finite. So let's see, where did we use that? Usually we need finiteness because we have like subtraction or summation in our proof. So let's see. Oh yeah, I think because of this. So for all j in N, there exists uj that is subs which contains E such that mu of uj is smaller than mu of E plus this. And then we also have this inequalities. And then we have this is we assume this is finite, therefore thus we can use the definition of the equivalent to find or to write explicitly like this. And here we assume this. And the question comes that what if the measure of E is infinite and how that will change our proof of this theorem? Because the theorem should still be held. The claim that the theorem still holds given that mu of E is infinite, has infinite measure. Now let's look at the case that when the measure of E is equal to infinity. Okay, there are two different strategies, and I will introduce the first one, which seems easier. Okay, so again, let's just restate the theorem. So E is mu measurable, so they're equivalent. So E can be written as V set minus N1, where V belongs or V is G delta, okay, and then the measure of N1 is equal to 0, or if only E is equal to H union N2, where H is F sigma, okay. Okay, so the first method is so again the reverse implication. So knowing this, it is very easy to conclude this. Why? Because V is in this and this is known size, so this is also like a Lebesgue still just measurable. Therefore, the intersection is Lebesgue still just measurable, and similarly, this is also Lebesgue still just measurable. And then we're done. So we're proving this implies this. And this implies this. Okay. So let's first prove. So A, B, and C. So prove A implies C. Okay. So define. So define En to be equal to negative n intercept E. Okay. And therefore mu En is finite. So before I was in doubt that why this is correct, but now I think I understand why. So because so when we were working with those approximation theorems, we previously fixed one Lebesgue test measure, and I noticed that each Lebesgue test measure corresponding to like up to a function with constant, like if those it is unique, if I know given that there may be a function that does the same thing as different from this function, but they're only different by constant. So in that context, the Lebesgue test measure has one-to-one correspondence with f, and f. Okay, and then if as you see like this, so mu of en is less or equal than mu of negative n, right, by the multiple measure. And we also know I should actually write mu f, because whenever we are talking about the Lebesgue test measure, it has since it has one-to-one correspondence with any with an increasing rather continuous function. This corresponds to the one-to-one correspondence with this function. So so we have this, and recall that since this is definitely in so I was trying to apply the definition of the mu, the function mu f. Okay, let's try. So I want to do f union. Let's see. Negative n. I want to include the negative n, so I need to be left a little bit more. So negative n minus 1 over j, or j comma n. I think this should be intersection rather than union, right? Okay. So why do I write this? Because this is in terms of h intervals, and right, and then this is equal to, because this collection is decreasing, so it's bounded. We can use bounded from above. We can use continue from above. So this is equal to the limit as j goes to infinity, mu of f negative n minus 1 over j comma n. And why do I want to write this? Because this is h interval, and which is in definitely in algebra, right? And then once we use algebra, we can actually this coincide with the pre-measure, so we can replace this as mu not f of this. Okay, so we have this. And notice that, recall that what is the definition for the pre-measure? I think it is mentioned in proposition 115. So this is equal to the limit as j goes to infinity of fn minus f negative n minus 1 over j. Okay, and then this is equal to fn minus the limit j goes to infinity f negative n minus 1 over j. And let's draw a picture. So this is right. So this is negative n, and this is n, and negative n minus 1 over j is here. Okay. And it's saying that as this converges to this, that it converges to f negative n. Well, not necessarily, because we only know that f is continues from right. So this is actually equivalent say that f is continuous from left, which is not correct. But the reason I want to do this is right. I just purely want to show that this is finite, so then we're done. So I will talk about a different way to think about this, where we don't have the awkward situation that to deal with this. Okay, but my goal is actually accomplished. Why? Because this is smaller or equal than fn, and because since f is from R to R, so it only takes finite values. So this is less than finite, and then we're in good shape. And then let's just prove using this first, and then later I will talk about others. Okay. So we have this, and then now, okay, apply the result on bounded set, which we have introduced at the beginning, right? So we talk about, we prove the theorem given the assumption that mu e is finite. Bounded set, okay. We obtain, so i.e. there exists hn in hn f sigma set such that E is equal to En is equal to Hn union n to n, where mu of n to n is equal to 0. So we have this. Okay, and now as you might, so if we do the union, so union of n, En is equal to union of this, right? Okay, this is equal to union of Hn, union union of n to n, okay? And then this is equal to E, okay? Hence that hinted us define H to be the union of Hn and N2 to be equal to the union of N to N. And because this, the null set is closed under countable union, so therefore this is still a null set, okay? And therefore we're done. Okay, we find the desired H and N2 to make that equality works. And another way to deal with this, I will, so let's, again, we want to show like A implies C, right? We want to show A implies C. So we have, so again, we define, okay, differently. So define E J is equal to J comma J plus 1 intersect E. And notice that mu of E J is finite immediately since okay, mu of EJ is upper bounded by mu of J plus 1. And then you can see this is H interval, so we can replace this as mu not F because the Lebesgue still test measure coincide with pre-measure on algebra. Okay, so this is J plus 1. Okay, and using the definitions of pre-measure, which is introduced in proposition 1.15, we have F J plus 1 minus F of J. Right. Right. So we have this. Okay. What else can we? What else? Okay. So this is definitely finite because F is final. F is real valued function. And okay. So we have this and apply again. Apply previous result. We have. So what is previous result? Okay, unbounded. Okay, there exists Hj. So again, it is F sigma set. Okay, such that E J is equal to Hj union N2J, where N2J is a null set, okay? And so union of Ej, which is equal to V, which is equal to the union of Hj union this, right? Which is equal to the union of Hj union the union of N2J. Okay, and this is equal to, so let's define, so we define H to be the union of Hj and union N2, and then N2 to be equal to the union of N2J, and then we're done. Okay, so we've proved A implies C. Now we need to prove A implies B. And actually we need to borrow, there are like some thoughts, different method to prove this thing, and we can prove let's just prove using the result from A implication from A to C. Okay, so given E is in M mu F, we want to show that there exists V G delta set such that V of G E is equal to V set minus N1, where the measure of N1 is equal to 0. Okay. So notice that this is, let me rewrite this. So V set minus N1, where V is G delta measure of N1 is equal to 0. So this is equivalent as EC, okay, is equal to V set minus N1 C. And so it's equal to V intersect N1 C. Okay. It's equal to VC union N1. VC N union N1. Okay. Okay, and so notice what I'm doing. So notice that EC is closed. Wait. No, actually, so apply the result on EC. Okay, so there is this H such that EC is equal to H union N2. Okay. So VC is F sigma N1 is no set. So this is H is F sigma. This is no set. And we're done. So while I was working on this, I also think about other ways to prove this. And I think it's slightly complicated, and I use that method, this exactly same method to prove A implies B and A implies C. So I just want to mention that a little bit. If you think there's a mistake, let me know. So I will prove A implies B. Okay, so A implies B using a different method. Again, we want to show what we want to show. Okay. So again, define So the way I define Ej to be equal to j plus 1 intersect with E. Okay, so we define this to be this. Okay, so and we discussed this before. This is finite. So by theorem 1.19 with bounded E, there exists for all J, there exists Vj such that Ej is equal to Vj union, no, set minus N1J. Okay, and E is equal to the union of Vj, which is equal to the union of Vj set minus N1J. So is equal to union of Vj intersect N1JC, right? Is equal to the union of Vj intersect the union of N1JC. Okay. So what I'm going to do next is I am going to define let's see, Vj. Oh, I'm sorry, I'm actually so define Ej is equal to this, and then finite the measure of Ej is finite. Okay, so by theorem 1.18, okay, there exists for all epsilon, there exists. So for all n, let's say, for all n in n, there exists because we want open sets. So I am going to use open set. There exists Uj contains Ej such that the measure of Uj is smaller than the measure of Ej plus 1 over 2 to the power of n. Okay, and then the measure of Uj is equal to the measure of Ej. Okay, and then the measure of the union. So I'm going to, for all there is Jn. Okay, so define, let's see, this is less than and the measure of Uj is equal to the measure of union of UJN, which is equal to measure of UJN, which is equal to measure of EJ, and EJs are disjoint, so the measure of union of EJ, which is equal to measure of E. Okay. Sorry, this should be this way. So we define the UJ such that this holds, right? So mu of UJ is smaller or equal than mu of E. And actually mu of E. Oh, mu of E. Plus 1. Oh, sorry. So this is smaller or equal than this plus 2 in epsilon or so let's just work, see what we get. So we have this, right? Plus this is 1, okay. Plus 1. Well, I do want this to be something with race. With epsilon. Let's do this. Okay, and then since we have this inequality, so define define U is equal to intersections of UJ. So the limit. Okay, I feel like I missed something. I missed something. I'll explain what I missed. So mu of U is equal to the limit J goes to infinity of UJ, right? Is equal to the limit mu of E plus epsilon. So I have mu of U is smaller or equal than mu of E plus epsilon. But actually, I think this epsilon should deal with J, so this becomes 0. J, I don't know. So if I change epsilon to 1 over J, 1 over J, 1 over J, 1 over J, 1 over J. So as so the limit is equal to 0. And therefore, and since E is always in U, why that is true? Well, recall that U is equal to the intersection of UJ, since E is intersection of U, E the subset of U j, which is equal to the union of n of ujn. A simple graph is like this is E, right? And then we're gonna partition it into small pieces. And then uj is equal to the union of those pieces. And of course it contains E. Okay, so we have mu of E is smaller or equal than mu of U. Therefore, mu of U is equal to mu of E. And therefore, mu of U set minus E is equal to 0. Hence, we showed the existence of such U. Okay, notice that, okay, okay, no, so N1 is equal to U set minus E, and this is a new set. Notice that uj is equal to the union of n uj, and so countable union, and each uj is open set. So countable union of open set is open. So therefore, when we define U to be the intersection, uj is like in the G delta set. Okay, now that reminds me about another method to prove this. Notice, like at the beginning, I was proving A implies C, right? And then to prove A implies B, I used the result of A implies C. And I think it is totally possible to use the same technique as I proved A implies C to prove A implies B. Because if we keep defining like this, we'll see, I'm going to use a different color just to distinguish. So there exists hj, instead of hj we have a vj, right? G delta set with ej is equal to vj set minus n1j. Okay, and then we have E is equal to the union of vj, which is equal to the union of vj set minus a1j, which is equal to union of vj set minus union of n1j. Okay. Now as I'm observing, so this is definitely a null set because a null set is closed under countable unions, but we need to show this is G delta set, and union of G delta set, I'm not sure if that is a G delta set. So it's basically saying that countable union of countable intersection, can it be countable? I think so. Countable intersection of the sets. I think so. I say we just need to spend a little bit more time to rewrite this. I'll try like 2 minutes. If not, then I'll just end the video because we have already solved this problem. So if we have G1 intersects G2, union G3 intersects G4, notice that this is in G delta, this is in G delta, and this makes in F sigma. No, this is in F G sigma. Okay. So we have G1 intersects G2. Okay, I think we are, so this is, so those two open sets, still open sets. So this is open. This is open. This is open. And this is open. So this is G delta set. And then we're done. So it is totally okay to use the strategy that we used to prove A implies C to prove A implies B. Or you can just use the result from A implies C to show A implies B. But there are many methods.